Welcome everyone, welcome in the very new lecture of AASHTO Design. In this specific lecture we will mainly try to understand that what are the basic method through which we can design, or what are the basic process through which we can design the model the flexible design, and also we will try to understand the AASHTO pavement analysis as well. AASHTO pavement design is used to determine the thickness of various layers for the given traffic, given material, given subgrade, and different type of a environmental condition. So the design of the pavement is done through the AASHTO pavement layer method. So according to the AASHTO, we will try to understand that how we can model and design for each and every layer. Okay, so before to go in a very detail, the aim of the design is to uh, to design a pavement through which we can carry a load, and we can divide and distribute the load from the top to the subgrade layer, and also it should provide the reliability to the vehicles as well as to the people as well. So the purpose of the AASHTO is number very one, the so that we can model and design for the dynamic repetitive load when we have a different magnitude and different arrangements such as tandem axle, tri-axle, and so on. And also the second purpose is to determine the different thickness of the pavement layer as well, and then also to nominate or to specify the quality of material through which we can achieve the specific loading condition, or the design or the life of the pavement, such as material rigidity and stiffness and so. So before to go in a very detailed, those are the design consideration which we need to consider, such as pavement performance, and which we usually try to understand that what is the structural and functional performance of the pavement, such as in structure we usually consider cracking and faulting and deterioration, while in the function we try to understand the riding quality, comfort, which we usually consider in terms of the roughness. While the next one is traffic consideration. So in AASHTO, traffic is considered in terms of ESAL, equivalent single axle load. At this stage we must assume the structural number, so we must check if the final SN is similar to the assume. So if we have the higher structural numbers, which means we have the stronger pavement, and if we have the lower structural numbers, that means that the pavement is less stronger, or its life will be little bit less as compared to the one which structural number is higher. Similarly, we have the material of construction. So like what type of material is actually needed in the top layer as well as in the lower layer. We have the roadbed soil condition, means such as roadbed soil condition is basically referring it towards the subgrade material, which performance or value or parameters we nominate with CBR value, resistance value, and modulus of resilient. Okay, and then we have the environmental consideration and drainage condition as well, in which we usually consider the kind of data that how much capacity of that specific pavement have to drain off all the water, such as rain, snow, etc., and so on. And then we have reliability, and then life cycle cost, and then shoulder design, and so on. The pavement design methodologies, if we go a little bit in history, so first of all, its concept came in 1950, so where we usually prefer or model the pavement through the experience method. Okay, but when the with the passage of time and after the technological advancement, the first time the empirical statistical model for the road test were derived in 1953, and then with passage of time, then the mechanistic approach appeared. But the only problem with the mechanistic that it need more comprehensive and sophisticated data from the laboratory method, while the empirical was completely based on the field observation and experience. But with the passage of time, when both theories were merged together for the purpose to derive the stresses and strain and deformation and so on, so the mechanistic empirical method was basically its design was based on the mechanics of material, which actually relate input such as wheel load or the output of the pavement response such as stress or strain. So the response value are used to predict stresses based on the laboratory test as well as the field performance data. But researcher also assume that mechanistic empirical model is function more accurately as compared to if we only use empirical or the experience method. So the mechanistic empirical method, which is also used as a ME method, is also used to also determine the different type of stresses as well. Okay. And then the last one, we have the mechanistic, where we actually based the whole model on the stresses, strain and deformation. So the if we use individually empirical method, it have also its own drawbacks and advantages if we use mechanistic. But if we use mechanistic empirical method, which is basically the combination of the field data as well as of the laboratory method, which is nowadays recommended according to Huang, who have done research in 1993, is basically nowadays used one of the most complete design methodology to support the AASHTO design. This is very famous and very detailed equation, which is called the AASHTO design equation. Okay, is here you can see different parameter. So we will start one by one. All those parameter which is mentioned it below, we will explain it one by one, and then in the last we will also try to resolve few tutorial as well, and then in the last we will also resolve this AASHTO design equation as well. First of all, we have the W18, which represent the design traffic load, and then ZR is standard normal deviation, and then we have S0, which is basically the value is derived from the modulus of resilient, and then we have delta PSI, which is the difference between the present condition of the pavement and of the when it is used for the service as well. And then we have resilient modulus, and then we have structure number. So first of all, we will try to understand each and every step which is used for the AASHTO pavement analysis method. The very first method, the very first step is to design the fixed design period. Okay, so that means that the pavement age is completely basis on the loading, material rigidity, stiffness and pavement thickness. So on the basis of all those parameter, we assume the design period that for example this is the service life of that specific type of the pavement. Second one is W18, which is also called the estimate design traffic. So an axle load is carrying of 18 caps and causing a damage effect of unity is known as standard axle load, which is denoted with W18. In the coming slide, we will also try to to understand that how we can count different type of traffic, where we also consider the average daily traffic, average volume, and so on. Okay. The third step is to analyze the ZR. So ZR is basically used for the normal deviation to compare the pavement different type of material condition. And then fourth one, we have the delta PSI, which is basically used for the like to understand the ability of the pavement to serve the traffic for which it is designed. When we talk about service ability, it actually refer to the ability of the pavement to serve the traffic for a period of for a specific period of a time. When we talk about the AASHTO method, when we talk about the service ability, so we have different type of conditions, such as you can see here, we have the two value. One is called PSI initial and another one is called PSI terminal. Okay, so initial is actually the value when the pavement were freshly built or constructed. So it is in the next slide, the chart is actually mentioned. So the fresh pavement initial service ability is almost between 4.5 to 5. But when we talk about the PSI terminal means when pavement were used for a few years of time, and it level were actually went down, and it need rehabilitation or to elevate the level, so that it should also work for a few more years. That PSI terminal value is actually based on the field observation from the different traffic and pavement. The fifth one is to evaluate the modulus of resilient and CBR value from the field according to the AASHTO road test, while the sixth one is to determine the layer coefficient for each and every one, such as base, sub-base, and subgrade. Similarly for the drainage coefficient as well. And then we can determine, and then we can resolve the AASHTO equation by putting all those values, and then we can determine the thickness and then compare it with different graph, table, and so on. As you can see here, when we talk about the terminal service ability, so this is a chart which is actually used for the field. So as you can see here, we have a section, then we have different type of a vehicle, and then we have a time, and then we you have like your own observation. So this is basically chart which is used to determine the present service ability rating according to the AASHTO standard. Okay, this is used for the pavement rating panel. Okay, so it's completely based on the slope variance, means roughness index, as well as also for the rut depth as well, which we usually count it in the inches, and also for the cracking and pitching as well. So crack is only the separation between two continuous medium, but when we talk about pitching, so we are trying to determine the crack in the vertical axis. So it means that we would like to see that how much is basically the length of that specific crack in the vertical direction, or you can also call it the intention or the effectivity of that crack in any specific direction. As you can see here, when we talk about the design service ability, where those charts were actually modified in 1993, it were compared the time with the present service index of that pavement. So as you can see here, when it were freshly built, so it were properly working, and its service ability were quite high. But with passage of time, that specific level reached to PT. So PT is basically our that level below which we actually need to elevate or do the maintenance for the pavement to improve, or to after the rehabilitation the pavement should be reused. Okay. uh, in the second picture, as you can see here, so this is the one where we not only consider the changes in terms of traffic, but we also consider the environmental factors such as swelling condition, such as infiltration of water or seepage or frost heave action and so on. As you can see here, the with passage of time, the analysis of period were actually coming down. So we have three different parameter, which is basically combination through which sorry we can determine the service ability index. So delta PSI is basically the total loss of service ability. Service ability in that sense is PSI means our present service ability. Basic means is when we build the very newly or fresh pavement, when we like provide it for the traffic operation after few years, when it level were actually went down or the cracks appear. So we need to determine a survey to determine that how much pavement is damaged or how much it lost its life. As you can see here, the total losses is basically the loss of the pavement quality, okay, which we usually consider it as a terminal service ability. So terminal is the one which is basically the same time. Okay. As you can see here, as I mentioned in the previous slide as well, when we talk about rigid pavement, its value is 4.5, but when we talk about flexible, it is 4.2. So theoretically, all those values are starting from 5, but according to the field observation, we can reach maximum up to 4.5 and 4.2. So the next factor is regional factor. Regional factor is the factor in which we consider the climate variation and climate condition, which we determine it from the road test, such as the roadbed material frozen, when we have different type of a condition, such as the Scandinavian countries, or specifically Russia, where we have completely frozen condition, or when the temperature went in the negative. Okay. And it also cover the when we have the complete material dry conditions, such as Asian territory, where we have summer and fall, and then we have spring condition as well. Okay. The regional factor is the AASHTO limit, which actually cover both the summer, winter and snow condition. As you can see here, the structural number is one of the most important element which actually use to express the overall pavement structural requirement, which is needed to sustain the design of the traffic loading. So it is basically denoted with SN. As you can see here in that specific figure, so D1, D2 and D3 is basically the different depth or thickness of each and every layer, such as surface, base and subbase. A1, A2, A3 is the coefficient of relative strength, okay, of the material. And then we have the another parameter which is used, M1 and M2 and M3. Basically M is the drainage coefficient of each and every layer. So if we would like to determine the structural number, so the formula is we need to multiply the coefficient of the material strength multiply by with the depth or the height and with the drainage coefficient. Then we can determine the structural number. We can determine the structural number individually for any layer, and we can determine it for the overall structural number as well. As you can see here is just the example. So just to give you roughly idea, if we have the aggregate base or we have the asphalt concrete, so how much thickness is actually needed if we have the design or estimated traffic equivalent single axle load. Okay, and then we can also determine the depth of each and every layer from the structural number formula. Okay, as you can see here, if we would like to determine D1, or if we would like to determine the coefficient of the thickness, so we can determine it from that specific equation. Okay, so next factor we have the reliability. What is reliability? Okay, reliability is actually a count for desire to determine the uncertain or certain, or it also express the degree of a certainty that a given pavement will perform. Okay, so in a very simple word, reliability is the kind of a term which we use to determine that this specific pavement will serve for how many years. Reliability consists of mainly two variables such as ZR and S naught. Okay, ZR and S naught. This is the design traffic load, how we can determine the 18 caps ESL. In estimation of the equivalent single axle load during the analysis period is required. So this value can be estimated based on few assumptions such as what is the average daily traffic in that specific year, and what is the percentage of trucks expected to use that specific facility, and also we will consider the analysis period, means the number of year for which pavement is designed, and then the fourth one is about that how much the annual growth is expected. Similarly, if we would like to determine the W18, which is equal to DD multiplied DL multiplied W18. So W18 is basically ESL, while DL is a lane distribution factor and DD is a directional factor, which usually determined from AADT and AADT. The next part is standard deviation. Standard deviation is actually the value through which we determine or derive the account of the standard variation of a pavement material and construction method. The probable variation in traffic estimation, the recommended value is between 0.4 to 0.5 for the flexible, while for the rigid it's 0.35 to 0.4. It's basically the estimation of variation for the according to the designer ability. The next one is about resilient modulus, which is actually defined or indicate the subgrade stiffness, and which is actually equal to the stresses divided by strain when we have the repetitive load. Okay. The difference between E and MR, the elasticity or the Young modulus and modulus of resilient, is the method of load application, where the MR is actually derived from the road lab test. So if we have different conditions, such as if the CBR value, California bearing ratio, is less than 10, so then we use the factor of 1500 and multiply it with CBR. But if the CBR is less than 1000, then we use it 2555, and so on. The next factor is drainage factor. So the drainage coefficient is actually the design capacity of the drainage system, which is typically expressed as a depth of water which should be removed within 24 hours. So like which we usually determine it with the inches or feet per day. So a drainage coefficient should be chosen that will which should efficiently remove the excess water from the pavement surface within 24 to 48 hours. As you can see here, we usually compare the water quality drainage with the water removed within the time. As you can see here in the lower model, so water under the pavement is one of the most primary causes of the pavement failure. So either if it's from the groundwater or from the rain or from the snow, it should if it became saturated and like weaken, that should also contribute a lot of percentage, which could decrease the CBR value. So the purpose of that quality chart is we would like to see if it's 1%, so how much effect it could provide or like affect our supportive layer. If it's up to 5%, if it's up to 25%, and then if it reach to 25%. This is basically the drainage factor, which we derive or determine it from the drainage chart, which we determine it from the inches per day within the time. So this is our very first question. We would like to design the numerical model. As you can see here, the to design the flexible pavement in rural highway, where we have 2.13 million buses and 1.33 million trucks, which should be facilitated. So according to the road test result, CBR value is 5, while P naught is 4.5, which is delta PSI basically, while the present terminal serviceability index is between 1.5 to 3.0, while the subgrade saturation is about 7%. Modulus of resilient for hot mix asphalt for the surface layer is 0.1, and then for the second layer is 0.17, and so on. The reliability index is 90%. As you can see here, we have the ESAL value, we have the reliability level of 90%, we have the S naught value of 0.55, and we have the delta PSI, which is 3.5. So we have a surface condition, and then base, and then sub base. The subgrade from the moisture separation at the subgrade level is 7%, at the sub base is 9, while at the base saturation is 10%. The value of CBR is 5%. As you can see here, this is our very first step to determine the traffic load or to determine the ESAL. So the formula for ESL, to derive it, we basically need the average daily traffic, the percentage of the trucks in the average daily traffic, and then we need the truck factor as well, and then we also need the growth factor in the year, and then DD factor, and then how much time for which we need to design the pavement, and so on. So coming to the very first step is we would like to determine the ESL. So we have only, according to the question or according to the tutorial, we have only two factor. Number one is buses, while second one is trucks. So we just simply add both of those factors. So we have the total ESL value. The second one, we have the to determine the modulus of resilience. So from the CBR value, we have the CBR of 5. Okay, so we have the CBR road test 1500 according to the formula. So we just multiply here the factor of 5. So this is the way through from which we would like to determine the normal deviation according to the AASHTO condition. As maybe you know that we have the local or like rural area. So according to that, you should consider it, either you are going to design for the urban area or for the rural area. So we have the reliability factor of 90, from where we can determine the ZR value. So the we select from the table of AASHTO the value of ZR. So if the like here is, you know, the reliability is 9, so the value of ZR is minus 1.282, while the S naught value is 0.55 according to the AASHTO table. So the fourth step is to determine the serviceability index. So we have the one which is like the one when we have the present condition, or we call the initial terminal service ability, which is 4.5, while the one we have PT, which is from 3 to 1.5. So we just select 1.5. You can also select the 3.0 value as well. So only for the understanding purpose, so it should become with P naught minus PT, so which is almost 4.0. This is the one chart which is already defined on the basis of resilient modulus of the each and every layer. Is you can see here we have the resilient modulus for HMA layer is 0.4, for the ACB layer, or for the UTB layer, or for the aggregate layer. Okay. So if we have the typical resilient modulus, we can also select the design or the resilient modulus, but we gonna determine it from here. Okay, as you can see here, we have the initial PSI value is 4.5 or 4.4. So the total number of year is 15. So from here we can determine the service ability losses for like 4.5 minus 2.5, which is almost 2, or we can do 4.5 minus 1.5, which is almost is equal to 3. Okay. As you can see here, we have the different trial performance period here. For example, if you would like to do it for 13 year, or for 8 year, or for like 9 year. So total service ability losses, which is happen due to the swelling condition, which we should also consider that one as well. We should also consider the traffic condition as well. So according to that, with comparing with the ESAL value, we can select the corresponding performance period of time. So to bring that specific figure, as you can see here, for example, we would like to model or design it for 13 year, but because of the losses in service ability due to different factor, it actually value reach from 13 year to 6.3. Similarly, from 9.7 to 7.2, and similarly from 8.5 to almost 8 years. So this is basically the performance period for which it will actually work. This is the one factor which only show that for example, if we have the ESL value is increasing with the passage of time, so the time will actually decrease. As you can see here, if we have different type of a parameter, and the losses or roughness in the pavement is increasing, so the analysis period, or the design period, or the operating period will be reduced. So this is also, we can select it from the nomograph value as well to determine the same formula. So this is basically stage number 1. We have reliability, which is almost 95 here. So we have overall deviation, which is 0.35. So we can select it from that specific graph, which is between 0.2 to 0.4. And then the third stage is to select the TL value, and then we have the estimated to determine the ESL, and then we have the effective roadbed soil, which is determined on the basis of modulus of resilient. And then in stage number 6, we can select the structural number, which we can compare it with the design service ability losses. This is just the way through which we can also do the analysis from the nomograph. So the question is it possible, if we would like to do the AASHTO flexible pavement design method, is it only valid for the flexible? Of course, we can also do it for the rigid pavement as well, but there is little bit different between both of them. As you can see here, the service ability index is almost the same. ESL value is also like the same, and then we have the determine the modulus of subgrade reaction, and then directly we jump to the slab thickness. Okay, but the flexible method is more detailed and little bit more complicated. So this is just for the better understanding purpose. So we can also provide the like this is a kind of a worldwide assumption which is used for the pavement thickness design according to the AASHTO tutorial. If we have the sub base value, okay, on the basis of CBR, we can determine and assign the different thickness to each and every layer. Okay, so such as if we have the service like the service ability index and then terminal and then reliability factor and so on, so we can select the different layer thickness. Okay, such as natural should be 3 inches and then sub base should be between 3 to 5, while these sub base should be 6 inches and so on. This is the recommended thickness for the flexible pavement which is used for the local road. So if but this is completely based on the CBR value as well as on the ESL. Okay, so on the vertical axis we have the factor of ESL, while on the horizontal axis we have the value of CBR. Okay, similarly for the collector roads,